Hi everyone, thank you so much for having me. My name is Maria Eckstein and I did my PhD with Ann Collins at Berkeley. I'm now working at Google DeepMind, but I will tell you today about my PhD work in hierarchical structure in mental representations and how humans potentially learn such representations through experience. Most of you here would probably agree that human minds have hierarchical structure. We think about problems at the level of seconds, hours, or years, each with its own constraints and goals, and all in parallel. Why would it be a good idea to do this, to represent problems in this hierarchical way? Likely because most real-life problems are extremely complex, and thinking about them hierarchically is the only way we can solve them. Think about crossing a street. If you represent the problem in terms of its basic features, each leaf on each tree, each pebble on the street, you won't be able to figure out how to cross the street. An infinite number of possible muscle movements is possible at every millisecond, and the road could change into any infinite number of states at every moment. This creates a combinatorial explosion of possibilities that makes planning extremely difficult because we are looking for a needle in a haystack. Another reason why we need abstraction is reward sparsity. Imagine that your teaching signal for learning how to cross the road is arriving on the other side without being hit by a car. This signal will only occur once you have successfully crossed the road, so it can't help you figure out how to cross it. The same problem arises in many situations, say learning how to play chess by winning a game, or learning how to cook by tasting the finished meal. It is obvious that we need other teaching signals to scaffold learning, and this is exactly what abstraction does. Abstraction clusters individual basic features into objects, so instead of representing the street in terms of pebbles and leaves, we represent it in terms of cars and pedestrians, and the planning problem has way fewer variables and becomes solvable. This is how abstraction can remedy combinatorial explosion. Abstraction can also break problems into subproblems. Instead of having to successfully cross the road in order to get a teaching signal, we individually learn how to walk, how to look for cards, and how to evaluate each step along the way. This is how abstraction helps with reward sparsity. Because it is so powerful, abstraction has been crucial in many different disciplines. In artificial intelligence, agents abstract over time, over states, or over the learning problem itself to solve complex problems using hierarchical algorithms. In psychology, at least since the cognitive revolution, many believe that mental representations are hierarchical, and in the past decades, more and more computational models have come out using hierarchical Bayes or hierarchical reinforcement learning. Neuroscience has shown that the brain itself is organized hierarchically. So for example, some regions are superordinate like the FPC, and control subordinate regions like the striatum in a processing hierarchy. The brain also represents more abstract information in more frontal regions and more concrete information in more posterior regions in a representational hierarchy. Now, it is interesting that even though almost everyone seems to agree that we need hierarchy to solve complex problems, we still don't know how to get hierarchy. In AI, the problem of getting hierarchy has its own name, the option discovery problem, because options are multi-step actions, so the building blocks of temporal hierarchy. Fodor also called this problem the puzzle of concept acquisition. The problem is that hierarchy only helps when the chosen abstraction captures the important aspects of a task, but it hurts otherwise. So an abstraction can be great for one task, say crossing the street, but horrible for another, say birdwatching. So the problem is how to find the optimal abstraction each time, which we know humans do quite well. There have been interesting suggestions for how to do that, for example related to intrinsic motivation. This is the idea that agents reward themselves for learning skills, which are useful for doing the original task. The crucial question is, of course, how to learn these skills without knowing yet what will be rewarded in the end. Oftentimes, agents mimic novelty-seeking or curiosity, so they reward themselves for seeing a new state or taking a new action to be more exploratory and enhance their chances at finding the final reward. What we wanted to do in this study was to look at how humans solve this problem. We had some hypotheses. We thought that humans would first explore a problem by randomly performing basic actions. For example, this girl is stacking building blocks on top of each other to see what happens. Next, we thought that some actions inevitably lead to consequences in the world that the human did not expect, just based on the rules of the environment. For example, this stack of building blocks starts to tip over after the girl adds the next block. We hypothesized that such an unexpected event triggers curiosity, and curiosity triggers more targeted exploration. So the girl is curious why the tower fell, and will build another one to see whether it will collapse. After enough targeted exploration, we hypothesize that the event will become predictable. When this happens, humans have learned a new skill. The girl, for example, has learned how to build a tower and how to predict when it will collapse. We thought that humans constantly learn new skills in this way, so that the basic action repertoire consistently expands and contains more and more complex actions. So the girl might learn how to build houses and bridges using her previous knowledge. How can we test this hypothesis? We designed a task that has a similar structure to the girl in the tower. We told participants that they could use this machine to make stars, which would give them points, and they had to collect as many points as possible. On each trial, the machine accepts 4 key presses, and when the keys are right, it makes a star. For terminology, I call each key press a sub-trial, and a sequence of 4 key presses, which can potentially make a star, a trial. Here, we press the first key, and it shows up as an orange circle. The goal is to create the orange star at the top by pressing the correct 4 keys in a row. You will notice this is a hard problem because with 4 allowed keys, there are many possible sequences. Participants are facing combinatorial explosion. However, we also made the machine responsive. Like in the real world, we do not just observe the final products of our actions, like a prepared meal, but also the steps along the way, like the chopped onions. For the machine, it did not just make stars at the end, but also showed the intermediate products along the way. Let's see what it looks like. When you press blue after orange, the machine displays a gear. The onions are now chopped. Because participants did not expect the gear, it should trigger their curiosity. What would you do next? Most people are most interested in pressing the orange key again, and then blue again, to see if the same event repeats. And indeed, we get another gear. At this point, we might get bored of this sequence. We have memorized that orange-blue leads to the gear, and added this sequence to our action repertoire. What should we do next? Let's start with purple this time, and then red. The sequence leads to red light. Let's see if this is reliable as well, and it is. We now have added 2 new sequences to our action repertoire, and gained the ability to produce a gear and a light. Obviously, participants in the real game need to explore much more to find these sequences, but for the sake of this presentation, let me also show you how to put it all together. On this trial, let's first make a gear, and then a light, and see what happens. Orange, blue, gear, purple, red, light. And the combination of produced an orange star, our final reward. Overall, the machine uses 4 keys, can make 4 stars, and 4 intermediate events. Each star is composed of 2 events in different combinations, so the orange star might be composed of gear then light, and the blue one light then house, etc. The gold star stays the same for 25 trials, which I call a mini block, and then changes. Each block contains a mini block for each gold star for a total of 100 trials. Participants first do a training phase with 3 blocks, and then a transfer phase, which I'll explain later, with 4 blocks. Here on the right, you see trials on the x-axis and accuracy on the y-axis. The colors indicate blocks, and the gaps between the lights are transfers between mini blocks. Gold stars are on the x-axis. You see that accuracy increases during the first mini block, which is the orange star, then starts again around baseline when the second mini block starts, with the green star is the gold star, and so on. So how do we check if participants created hierarchical representations? We first wanted to know how participants responded to unexpected events. Would they ignore them because they are not rewarding? Or would the events trigger curiosity and affect behavior? To test this, we first found the first trial in each mini block in which participants discovered a new event. For example, they pressed orange and then green and got a gear for the first time. This should be the moment of maximum surprise. We then looked at how long participants took to respond after this event as a measure of how much they were processing it. The figure at the top shows trials on the x-axis and response times on the y-axis. The x-axis is aligned to the trial in which the event appeared for the first time, and the red line shows the response time right after this event. The red peak at 0 shows that participants indeed slowed down significantly. The error bars are so large because of between participant variance, but it is very consistent within participants. Response time slowing often occurs when participants are surprised or after they get feedback, so this suggests that participants process the event. But did events affect behavior? To test this, we looked at whether participants repeated the sequence they just discovered. The figure at the bottom, The figure at the bottom shows aligned trials on the x-axis, and it shows how often participants repeated the sequence they just discovered on the y-axis. The red line is a baseline, a random collection of 2 key sequences that do not create events. The blue line is the interesting one. These are the 2 key sequences that lead to events, which we call the valid 2 key sequences. The blue line is much higher than the red one, so participants do repeat sequences that just discovered more than other sequences, showing target exploration. This shows us how participants responded to individual events, but how does this affect behavior and learning more broadly? We first wanted to know if participants expanded their action repertoire, like we hypothesized. In other words, that they add new 2 key sequences. To test this, we focused on just the first mini block and checked whether the frequency of valid 2 key sequences changed over time. The figure at top shows trials on the x-axis and the fraction of each sequence type on the y-axis. Each trial has space for 2 sequences, so the maximum is 2 here, not 1. We see that participants started out with equal proportions of valid and invalid key sequences, as we would expect, but after just a few trials, the balance shifted and participants chose more and more valid sequences. This suggests that their action repertoire now contained 2 key sequences. Lastly, we wanted to know how participants perceived these 2 key sequences, as a combination of 2 individual actions or as one new action. To test this, we looked at response times patterns. The figure at the bottom shows the 4 subtrials, so the 4 key presses, of a trial on the x-axis and response times for each key press on the y-axis. We see a clear slow, fast pattern. So the first 2 key presses are chunked together and the last 2 are also chunked together. This suggests that participants executed 2 key sequences in one go rather than as 2 separate actions. For all these analyses, we only used incorrect trials, i.e. trials in which participants did not win a star. If we had used correct trials, they would naturally have a larger proportion of valid 2 key sequences, because only valid sequences lead to stars, so it's important to exclude them here. We now know that participants created hierarchical representations. They used actions that extended in time, treating 2 key sequences as just a single action. Can we say something about how this affected learning and behavior? To test this, we added a transfer phase, which either messed with the lower level of the hierarchy or with the higher level to see how each affected behavior. I'm showing the training rules for the orange star on the left here. Orange and blue lead to the gear, purple and red to the light, and together they create the orange star. To mess with the lower level, we changed some 2 key sequences. In this example, we now need to press red and then green to get the gear, instead of orange and then green. But the combination of events for each star stays the same, so we need the gear and then the light to get the orange star. This is a low-level manipulation because we modified the lower level of rules, the 2 key sequences. To mess with the higher level, we exchange the entire 2 key sequences with each other. So here, we now need to get the gear and then the flash instead of the gear and then the light. But the 2 key sequences themselves stay the same, so orange and green have always led to the gear, and green and blue has always led to the flash. This is a high-level manipulation because we modify something that is happening at the level above the 2 key sequences, at the level of combinations of 2 key sequences. We did not tell participants when the transfer phase started, and there were no visual cues, so they just kept pressing keys for stars and the rules changed in the background. What did we expect would happen? In the low transfer, we manipulated the extended actions participants had just learned. We expected that that would create big difficulties because the extended actions form the building blocks for stars. Participants basically had to start from scratch in terms of the hierarchy and relearn the lower level before they could reach the stars again. In the high transfer, we only manipulated the higher level, so participants could still rely on the lower level they had just created, the 2 key sequences. They just had to figure out that they had to combine them differently now, which should be much easier. So what actually happened? On the left figure, I'm showing average accuracy on the y-axis and trials are on the x-axis, comparing the low and high transfer phase. We see that participants indeed performed much better in the high transfer than in low. This suggests that the lower level 2 key sequences were more consolidated and harder to relearn, and that the higher level combinations of these sequences were more flexible and easier to relearn. The inverse was true for response times on the right, so participants were both slower and worse at the low level manipulation. There was no speed accuracy trade-off. In other words, the different levels of hierarchy really seem to play different roles. The lower levels seem to support stability and the higher flexibility. In conclusion, we try to get a window into how humans created hierarchical mental representations, piece by piece, in a structured environment. When the environment is responsive, in this case creating intermediate events, participants can learn meaningful temporally extended actions because they are curious about events and systematically explore them until they know how to control them. In such environments, hierarchy is very useful for exploration. Participants don't need to combine actions randomly and are automatically in tune with the structure of their environment. This helps them reach faraway goals and explains how we might learn complex everyday actions like crossing the road without having to observe the final outcome first. Our next step is to apply a specific computational model to this data. We already presented this model at a NeurIPS workshop a few years ago. Basically, the agents experience surprise when unexpected events occur, which triggers curiosity and the creation of options, i.e. multi-step actions. We also need to run additional versions of this task to learn more about the intricacies of intrinsic motivation and clarify the role of structure. With this, I would like to thank the CCN Lab, my advisor Anne, and Amy and Aram for their help with this project, the MIMH for funding, and all of you for your attention. I'm looking forward to your questions. Thank you.